Hi there. We are talking about section 3.3, curve sketching. We're going to tackle this first learning objective in this video, determine horizontal and vertical asymptotes of a graph. So you probably have seen some kind of definition of this. Most standard pre-calculus or college algebra courses discuss asymptotic behavior. But you may or may not have actually seen definitions in terms of their limits. So since chapter 2, end of chapter 1, we were talking about limits of functions, including limits to infinity and limits that have an infinite value. This is where we start to see the behavior of those graphs sort of come out. So we say a function has a vertical asymptote at some value, x equals a, if when we approach from the right side toward this value, we get positive infinity, or if we approach that value from the left side, we get positive or negative infinity. So a visual on this, if we take a look at this picture, for instance, the kind of behavior we're looking for is approaching some x value, does this graph explode either straight up or straight down? And there is one value on here. It looks like at x equals -2, we've got this kind of split. As we approach it from the positive side, then the graph shoots upward. As we approach it from the negative side, the graph shoots downward. So that's going to imply that either one of these technically would work, but we've got a limit that heads toward infinity from either direction. We also note that this should happen at x equals 0. This is the less standard case, but from the right side, it seems to be approaching some finite value. However, from the left side, the graph seems to be dropping downward without any indication of stopping. So we're going to infer that that implies this limit is negative infinity from the left. So because it approaches that way from one side, that's actually enough. What we often will do is include in our graphs some kind of perfectly vertical line, just like the one I'm throwing out here, to indicate where those asymptotes might be. That's not necessary, and in fact, some programs, Wolfram Alpha included, and lots of calculators, will graph a straight vertical line for the actual function. They'll draw, like in this case, it would be a nice blue or kind of purple-ish vertical line, and students will sometimes think that this is actually part of the graph. So the asymptote is a feature that gives us information about the graph, but this vertical line is not actually a part of the graph of the function. In fact, specifically, the function is undefined at that value for -2. Okay, so there's also horizontal asymptotes. We can talk about other kinds of asymptotes too, slant asymptotes and so forth, but the horizontal and vertical are the ones that have the most interesting kinds of results. So a horizontal asymptote occurs at some output y equals a if the result of this limit as x goes to infinity is a. So this is an interesting parallel to vertical asymptote situations. The vertical asymptote, we were asking for a to go to some concrete value, and then we're curious if the output would be infinity or negative infinity. Here the roles are reversed. Now we're saying if x goes to infinity or negative infinity, we look very far to the right or very far to the left on our graph, does the output approach some finite value? So let's borrow that same graph again. And this time we're supposed to say, as x goes really, really far, say out to the right, does this graph appear to be approaching some concrete height, some finite value? And if we believe that this trend continues, maybe the graph is getting closer and closer to the horizontal axis as we go out to the right. We should also check to the left. So as x goes to negative infinity, we get a similar kind of behavior. So that means that we're also approaching the x-axis in the left direction, which it gives us the same information, basically. It's still telling us that the graph appears to have a horizontal asymptote at y equals 0. So again, that's because the graph approaches a finite value, that is not infinity, or a number that doesn't exist, as we go to the left or the right, far left or far right of this graph. So let's try an application problem with some asymptote stuff. So we're going to say that if we want to remove x% of pollutants from some area, then this is the cost function. This is actually modeled off of some data from a 2007 study of costs to remove stuff using sand filters. At any rate, so here's our cost function. C is in thousands of dollars. X is the percent that we want to remove. And then our instructions are to find horizontal and vertical asymptotes. And then the most exciting part, of course, interpret them. Okay, so it doesn't matter which we start with, but let's try horizontal to begin with. So just by definition, we're going to grab these limits as x goes to infinity, x goes to negative infinity, and see what happens to the cost function. So I'm using c, of course, here because I don't have an f of x, but I sure do have a c of x function. So limit as x goes to infinity of this says, okay, so what happens to 800 over 100 minus x as x gets really large? Well, let's see if we can consider this numerically. So we'd have, as x is really, really big, 800 on top doesn't really change at all. On bottom, however, we'd have x getting really big. So let's imagine x was a billion or something. Then 100 minus a billion is some large negative number. And that's basically enough information, because if x continues to get larger and larger, the denominator continues to get more and more negative, then it doesn't matter if this is a positive or negative number on bottom. As we get a very large number, either big or big positive or big negative, then this whole fraction is going to head toward 0. So that's convenient. There's at least one indication of a horizontal asymptote, because what we're looking for here are concrete values, that is, finite values, non-infinite. And so we check the other direction, but here's a similar scenario, not identical, but we have 800 on top, and now as x goes to goes to negative infinity, our denominator is now 100 minus some big negative number, 100 minus, say, negative a billion. And we have a very similar circumstance. It's still a large number, this time it's in the positive direction, but that's actually the same result. If we take 800 and divide by a billion, then a trillion, and then quadrillion, these numbers are getting closer and closer to 0. So these numbers don't have to agree for any given function, but for this one, this cost function, both out to positive infinity and negative infinity, the outputs for the limits are 0. Okay, so vertical asymptotes, we're discussing a particular type of function in this case. So I'm always a little bit reluctant to talk about strategies that only apply to particular types of functions, but we're gonna make use of it in any event. So what we're looking at basically is that for a rational function, we're gonna find places where the domain errors occur. That is where we get undefined values. Those are the most tempting opportunities to run into vertical asymptotes. They don't always result in vertical asymptotes. Sometimes there's other interesting things there, those fun graphs where we see holes, like a little open circle in the graph that we've drawn before. But sometimes they will result in this. So here's what we're going to do. We're going to take our cost function, and we're going to note that when x is equal to 100, then this would be 800 over 0. It would be undefined. So basically, we're just using this as an indication to say 100 is a good tempting spot to look for vertical asymptotes. So vertical asymptotes are a little more challenging than horizontal because we have to pick the input to go looking for the limit. For a horizontal asymptote like we just did, we're always forced to let x go to infinity, x go to negative infinity, and see what that limit looks like. Okay, so we're going to test out 100 because we see that it's undefined. We'll do it from the left side and from the right side. So again, the consideration is as x approaches 100, but for numbers that are slightly larger than that, then again, just thinking kind of numerically or qualitatively here, we'd have 800, because the top doesn't get to change. And then on bottom, we'd have something very close to 0. But if x is very slightly larger than 100, 100.001, then 100 minus that is going to be some small negative number. So, and by small, I mean close to 0, negative 0.0001 or something like that. So a small negative number, however, means that we take 800, divide by something small and negative, that's going to make our outputs very large and negative. So what that's going to imply is that this graph is going toward negative infinity as the x values continue to get closer and closer to 100, but from the right side. If we try the same thing with x values approaching 100 from the left side, we have a similar kind of qualitative situation that we can draw out here. So we've still got 800 on top, that doesn't get to change. We've got x approaching 100, but from the left side, so 99.99 is something I should think about. 100 minus 99.99 is going to get close to 0, but taking away 99 something is going to mean that this number is still positive on bottom. So the qualitative thing that I can write is that as x gets closer to 100, but from the negative side, that is 99 point something or other, then we're going to have small positive numbers in the denominator. And if you divide by a small positive number, the overall fraction is something big. If you divide by 0.0001, then your fraction is some large positive number. So what we're going to end up with is infinity for our limit there. We actually could have stopped here, if you recall. We could have noted that as soon as we see that there is an infinite limit, negative or positive, as we approach 100, then there must be a vertical asymptote there. So it doesn't actually matter for us to check the other side of this, but it's good practice anyway to remind ourselves how to find these limits. So, and there's just a written reminder of that. So we only really needed to figure out that one of these limits was infinite. We don't have any other places where the cost function is undefined. X equals 0 or x equals 100 was the only one. So we can conclude from that that there shouldn't be any other vertical asymptotes. This is a little bit wishy-washy, but we're basically saying if the function isn't undefined there, then it's not a good place to look for vertical asymptotes. There are certainly cases we can create Frankenstein's monster kind of functions that patch stuff together and have vertical asymptotes, but are also defined in a certain spot. But in general, when we're just given a formula, that's not going to happen. So we were also supposed to interpret our values. We figured out vertical and horizontal asymptotes, but we're also supposed to say, what does that mean in some context? So, okay, so a horizontal asymptote says that if x approaches infinity, so that is our inputs, percentage of pollutant removed approaches positive or negative infinity, so these were our x's, then the claim is that the cost to remove these pollutants gets prohibitively large. Or sorry, it gets closer and closer to 0. So just wanted to change colors there. So our horizontal asymptote was y equals 0. So we're saying as x gets close to positive infinity or negative infinity, then the cost to remove this is getting close to 0. That's sort of a weird conclusion to come up with, but keep in mind that it actually doesn't really even make sense for us to do this. So value of x approaching infinity doesn't really make much sense, because if you think, okay, the least amount of pollutants we could remove would be 0%. That's the farthest left that we could go. And the most that we could remove using these sand filters was 100%. So going to negative infinity or positive infinity is not actually a meaningful situation here. So actually, a perfectly valid conclusion for this particular problem is that the horizontal asymptote has no interesting interpretation, because it doesn't make sense for us to go to negative infinity or positive infinity with our inputs. Vertical asymptote, on the other hand, so at x equals 100, that means that percentage of pollutants to be removed as this approaches 100%. So let me get consistency. Go back to red. So percentage of pollutants removed, that's our x value. And remember, we wanted x to approach 100, so we're approaching 100%. We could say from the left, maybe that's the thing that makes the most sense in this application, but regardless, as we approach 100%, then the result from this is that the cost approaches infinity. Maybe this does have some meaning. Basically, as we try to get closer and closer to removing every last little molecule of whatever pollutants are in there, essentially we're running cost up to something prohibitively difficult, something that would require an infinite amount of money. So you may disagree with the model. There may be some cap on actually removing every last little bit of pollutants out of there. So it may be super expensive, but not actually infinite. But this is what the model predicts. If we try to remove 100% of the pollutants, it's going to cost an infinite amount of money. Okay, so that's it for our vertical and horizontal asymptote video. We'll be back to discuss a strategy for graphing functions using all their features in the next video.